Audience? What are you doing, audience? I mean, there's a sink right there. How did you turn that on? That would have overflowed. It would have poisoned you, audience. You know you're allergic. Gosh. Anyways. After we saved your life there. Oh, you can thank me later. Thank me later. Anyways. Today's video is actually going to be about the liquid fluoride thorium reactor. Now, Zach Wakeman out at WLC, we were just talking about all the different advantages and whatnot of the liquid fluoride thorium reactor, and he was like, I'm not sure, he wanted to know all of them, and I'm not sure we got all the way through them. So today's video, we're just going to go over all of the different little intricate advantages to the liquid fluoride thorium reactor. And I know I'm kind of doing this backwards. I'm not explaining the reactor first. But advantages, yeah, whatever. So, many of the advantages are based on the fact that this is in the liquid form. Now, other previous reactors have solid fuel, right? So you've got to take the fuel out of the reactor to reprocess it. But with the liquid fuel reactor, you can reprocess actively, like during the... You can just reprocess, you can take materials out that are extremely rare, the fission products that are generated, and this is the base source of most of these advantages. So, advantage number one, this whole group of advantages is going to be based on isotopes, right? So, different forms of atoms that don't exist in nature that decay off relatively quickly. So the first one is going to be medical, right? So what applications does this have medically in treating cancers? First off, you can create, this reactor will create in its operation medical molybdenum-99. Now what that's used for is, you need molybdenum-99, or technetium is what it's is what the form you actually, it's complicated. So you need it to do diagnostic procedures on patients that may or may not have cancer. So you just would take this out of the reactor, and then you basically use it in medical practices, inject people with small amounts of this stuff to be able to do diagnostic procedures on those people. Some other isotopes are iodine-131. If you've got thyroid cancer, iodine bioconcentrates in your thyroids, and you can perform chemotherapy very precisely and not have too many ill effects, and just take out your thyroid cancer. And then another, the final and most important medical isotope would be bismuth-213. Now, the cool thing about bismuth-213 is a couple cool things, actually. It's on a dead decay chain, right? So the decay chain it's on does not exist in nature. So it's on the uranium-233 decay chain, which is the main fuel for this reactor. And you can actually take this medical isotope and attach it to an antibody. Now what this antibody does is it goes and it just attaches itself to the cancer, right? So if you take a bunch of bismuth, the special isotope, and attach it to a bunch of the antibody, it will go and attach itself to the cancer cell, and then the bismuth will decay, and it'll send out a knockout punch to the cancer cell. It's like the difference between beta and alpha decay, which is part of the difference here. It's like the difference between a dumb bomb and a smart bomb. With this medical isotope, you've got a smart bomb against cancer. You're able to precisely take out only what you want and only the cancer cells. And that's a real big advantage, because chemotherapies normally have a lot of pretty bad side effects. It speaks for itself. But this would be able to allow us to advance chemotherapy to where we could take out cancer without having nearly as many of the ill side effects. It's like the smart bomb versus the dumb bomb, right? Bomb a whole city to hit the factory, or we drop one down the chimney or the ventilation shaft and just... There you go. So those are the medical applications of the liquid fluoride thorium reactor. Some other applications of its isotopes are heat generation. So strontium-90 in particular is a good one. You'd be able to isolate strontium-90, and then you'd be able to sell it off to remote facilities like Antarctica's McMurdo Station. They've got a little research facility at the South Pole. I think they test stuff cold. It's Antarctica. So they need a lot of heat down there. Now, the only way they can get themselves heat is if they fly in diesel fuel, right? So we're going to fly all the way from the tip of South America all the way down to the pole, South Pole, to deliver fuel. And we're going to burn up like 4 gallons of fuel to deliver 1 gallon. It's inefficient. So strontium-90 would have an excellent application there for isolated heating units. Also, for heat generation, plutonium-238. Now, plutonium-238 is completely different than plutonium-239, the stuff we use in bombs. Plutonium-238 is worthless for bombs. Plutonium-238, what we could do with it, isolate it, and then what NASA is desperate for this stuff, right? We don't have any of it left right now. We're out of it. And there's really no way to make more unless we use this reactor. So plutonium-238, what we could do is use it to fuel our deep space explorations, like deep space exploration missions, right? So the United States is unique in the capability of sending space probes beyond the asteroid belt, all because we had some plutonium-238 on hand. Now that we don't have any left, we can't really go beyond the asteroid belt any longer until we get some of this to generate power on those spacecraft. So there's basically all the isotope advantages. I made a list. I'm getting ahead of things now. Audience, you gotta give it to me. Anyways, so, dang it. Okay. Distillation, right? Current nuclear reactors run at about, what, Alyssa? I'm busy. Current nuclear reactors run at about 300 degrees Celsius, right? So, to generate power or electricity from heat, you need to be able to dump waste heat somewhere. Now, it's general to gas, coal, anything. It needs to dump waste heat. Like, it needs to get rid of some heat somewhere. So, current nuclear is about 300 degrees Celsius for its heat generation. That means it's very inefficient. But this stuff's about 700 degrees Celsius. So with that bigger temperature gradient, it actually can be 50% efficient instead of 35%. Right? So, and also because of that higher temperature, it's got another unique advantage as well. Upon dumping its waste heat, it can desalinate seawater with that heat, right? So we can boil some seawater, also potentially generate some sea salt, but we can boil some seawater off with the waste heat, and then we can collect that and have a bunch of fresh water. Now, I understand that most problems in the Middle East, although like most people say they're based on oil, most of these problems are based on not like water supplies. A lot of the conflicts, it's all about water out there, and for good reason. So, if we could have a system of liquid fluoride thorium reactors, we could generate a lot of fresh water that could be used for agricultural purposes and just everyday consumption, not only here in places that are conducive for it, but as in the Middle East and places like that as well. So it's got a real big potential there to solve some geopolitical problems and solve the big water problem that we're facing, not having enough fresh water. And by the way, it does that at no like economic detriment, right? It would only be the cost of building the distillation plant, right? So, I mean, it's not going to cost like the heat's going to be free. That's the biggest expense of distillation. It's got to burn a lot of natural gas. But with this, you're basically getting fresh water for free on top of all the other stuff. Then we're going to do, how about next we'll do synthetic fuel production. because you can get energy at like 3 cents per kilowatt hour out of this technology, that's so much better than coal, which is like 6.5 cents, and gas, which is also around 6.5 cents. You can get energy for such a cheap and inexpensive price. You can make synthetic fuel out of air. Now, number one would probably be ammonia. It is also a fertilizer, so that'd be beneficial to farmers. You'd basically be making ammonia at half price. Now, what ammonia is you take nitrogen out of the atmosphere, which is also 78% of the atmosphere. You split water, and you take that hydrogen gas from the water, you combine it with the nitrogen gas, and you generate ammonia. So you're making ammonia, and then because you can make it so inexpensively, you can then now use it as a synthetic fuel in cars. So now you can have an internal combustion engine with 0 emissions, all for, I think the estimate came out to be $2 a gallon for an ammonia equivalent, right? So this much gasoline this much gasoline equals this much ammonia. This much ammonia, this much gasoline will get you this far. Has this much energy. This much energy in ammonia form would cost $2, right? So it'd be like paying $2 a gallon for gasoline, except you're using ammonia. So, and then different fuels that you could create from air. You could also make dimethyl ether, although you'd have to go after the rarer carbon. So now you're making dimethyl ether could be used as a direct replacement for diesel fuels. So you can make a lot of different kinds of synthetic fuels right out of the air we breathe and be relatively inexpensive because this form of energy could be so inexpensive. So that's most of the advantages. Good thing I wrote them down because there's several more. So you can basically power everything in society: cars, trucks, planes, trains, and generate electricity. So there's not much else. There's really nothing that you couldn't power. There's really nothing you couldn't power with this technology. So I've got distillation, space travel, medical, exploratory. Oh, valuable byproducts, right? So your fission products are going to be whole different kinds of stuff off the periodic table. Some of that stuff is very, very, very rare. You can make a little bit of rhodium and platinum, I think. I might be wrong about that one. But I know you can make neodymium. Now, if you remember, well, no one really remembers, only old people. Back in the day, in the 80s, we had these huge headphones that were like headphones, It's like whole surround your face headphones. But now we got these little earbuds. Well, what made that possible is neodymium iron boron magnets. So there's a little rare earth element called neodymium, which you need for electronics, that you could get out of this reactor as a fission product. You could do ship propulsion very easily with this technology. You could drop one of these reactors in a ship, and then it would be completely autonomous, and you wouldn't have to refuel it for a very, very long time. Any maintenance that you would have to do on the reactor would be so prolonged that the ship also would need maintenance. So it wouldn't decrease, the amount of times the ship would have to go in to be maintained wouldn't be increased by having the reactor there. So that's another great advantage. You can completely power all the world's large cargo ships off of this technology. And then the last one is changing thorium regulation. If we were to promote this technology, the liquid fluoride thorium reactor, we would be able to, if we were to promote this, maybe we'd be able to get the thorium regulation in the United States changed as well. Thorium right now, if you take it out of the ground, has to be considered a nuclear waste, right? So if you take it out of the ground, boom, it's a nuclear waste. You haven't done anything to it. You just take it out of the ground, it's a nuclear waste. It's completely ridiculous on 2 points. One, it's natural stuff. You moved its location and it became a nuclear waste. That's the first ridiculous part. Second, it's got a half-life of 14 billion years. Now, if you only think about half-lives, they're inversely proportional, right? So, or yeah. So the longer your half-life, the less radioactive you are. You're still bleeding off the exact same amount of energy, but it's the rate at which you do that. So if you have something that's radioactive for a day, it's very, very, very radioactive. If you have something that's radioactive for a million years, it's not going to hurt you at all. It's just bleeding off that energy too slowly. So thorium is not, it's hardly detectable on the radioactivity scale. So there's no radioactivity scale. I guess there kind of is with rads and whatnot, and millirims and rims. Anyways, so if we could change thorium is also found with rare earth elements. Now, we had a little conversation about this. Rare earth elements are absolutely necessary for building electronics and whatnot, right? So right now you can't really mine thorium in the United States unless you're willing to deal with very, very strict regulations. But if you were able to change that, we could start mining for rare earths in America because they always come up with some thorium, right? So that thorium's preventing us right now. Now we could mine with rare earths if we promote this technology. So, interesting story about thorium regulation and rare earths. China initially satisfied everyone's diet in the world for rare earth elements. They basically went out there and like, okay, we'll sell you rare earths cheap. And everyone got hooked on Chinese rare earths. But then China changed the regulations on that. They said, hey, you're going to have to pay a big excise tax if you want to get rare earths. Or you could relocate to China and not pay the tax. So to things like this iPhone, like they're made in China because China got the world addicted to its rare earths and then said, hey, you're going to have to come to China to build that or pay an extremely hefty fee for that stuff. So that's the way China took over the electronics market. And by promoting this technology, the liquid fluoride thorium reactor, we could potentially change the regulation on thorium in the United States at the same time, thus opening us to mine for rare earth elements, and thus bringing back the electronics market to America. So I hope you found this informative, fun, super fantastic. Those are the advantages of Lifter. I know I'm at almost 18 minutes, which was a ridiculously long time for a lazy vlog. So I'm going to let you guys go. Have a good day, week, month, time at National Convention. And, oh, I forgot something. I've forgotten it. But I didn't. Outro. Darkness, then redness, then white. That was a pretty crappy outro. Anyway, see ya.